know, when you have a molecule there, you have to know whether it's polar or non-polar, based on the geometry, based on the electron distribution. In polar molecules, we would have interactions between ions and molecules with what we call a permanent dipole moment, meaning there's a difference in polarity. And water molecule is a good example there, because oxygen here is much more electronegative than hydrogen. As a result, this end of the water molecule would bear more negative charge. The other end of the water molecule near hydrogen, that's the part where the water molecule would bear partial positive charge. Okay, so water molecule is considered a molecule with a permanent dipole. There is a permanent separation of charge between the oxygen atom and the hydrogen atom there. Now, if you have ionic compound, you throw them in there, well, ions in the ionic compound, positive charge, negative charge, will interact with water molecule. Okay? That's the primary reason why table salt dissolves in water, because in table salt you have sodium ion, you have chloride ion. When you put them in water, their interaction between the water molecule and the ions in the ionic compound will pull them apart, resulting in the dissolution. Okay, so that would be the strongest intermolecular forces there. So ion-dipole interaction, that's the strongest. And then if you have a polar molecule versus polar molecule, if you have two water molecules, and the previous example there, when you have two HCl molecules, they will also interact with one another. So that's the second type of intermolecular forces there, and that's the molecules with permanent dipole interact with one another. That's the second strongest type of intermolecular forces there. Now, one special type of intermolecular forces, we call them hydrogen bonding. There is a condition where hydrogen bonding can occur. So you have to know under what condition. What are the atoms requirements? What are the elements involved, required in order for molecules to be able to interact through what we call hydrogen bonding? So these are the three types of intermolecular forces involving polar molecules there. And water as an example, and again, we say, when you look at the geometry of the water there, water molecule we say is bent. But there are two lone pair of electrons on the oxygen atom there. Okay, so there are four groups of electrons, four different types of, four different pairs of electrons on the water molecule, on the oxygen there. So in this case, then you have two lone pair and two bounding pair. So the oxygen atom is more electronegative in this case, and it's going to bear a partial negative charge. So we use delta negative representing partial negative charge. And then where the hydrogens are in the water molecule, they bear partial positive charge. So the polar nature of water provides for attractive forces between the ions of water. So in this case, and the solvation is the term that we use, solvation of the ionic compounds in water. If you have, say, sodium chloride thrown into water, now sodium ion bears positive charge. Okay, so in this case, this positive charge will be attracted to the negative end of water. So oxygen will be moving towards sodium because of that positive negative charges there. Okay, and if you have a cation there, a cation will be attracted to the negative end of water. But if you have an anion, a chlorine, sodium chloride, you have a chloride ion, then you have a large ion with a negative charge there. There are positive ends in water molecule. The positive ends of water molecule will be attracted to the negatively charged ion there. So this is an interaction between basically the electrostatic attraction there. Positive, negative, and they are attracted to one another, resulting in the dissolution of sodium chloride. That's why many ionic compounds are water soluble when you put them together because of this kind of interaction. And that said, you also need to remember there are many other ionic compounds. The attraction between the negative ion and positive ion are so strong when you throw them in water, this interaction is not enough to pull them apart. That's why when you have superchloride and you put it in water, they remain in the solid form. The majority of it will not dissolve. Versus sodium chloride, well, sodium chloride, the attraction between chloride ion and sodium ion is not as strong as between super ion and chloride ion. So superchloride does not dissolve in water, sodium chloride does because of this interaction. Now, if you look at the size of the ion versus the amount of energy involved for the dissolution, we use the term enthalpy of hydration. When you try to dissolve something, there's a certain amount of energy involved in there. So this is a group 1 element, or the ions of the group 1 element. We have lithium, sodium, potassium, and so on and so forth. And the size is increased. Well, that's one test question there. Going from top to bottom within the same group there, the radii is increasing, so the atoms are getting bigger and bigger, and also the ions in turn also is getting bigger and bigger. So as we can see here is that as the size of the ion increases, it becomes easier and easier to dissolve them. So the enthalpy of hydration is actually lower and lower. Okay, so you go, again, the negative sign only indicates negative 515 in pure mathematical sense is a smaller number than negative 263, but in chemistry, the negative sign only indicates the direction of the energy flow. We're talking about the absolute value here, 515 kilojoules per mole versus 263 kilojoules per mole. And when you dissolve lithium chloride, for example, it's going to release 515 kilojoules per mole of energy. When you dissolve cesium chloride in water, it only releases 260, about half of, well, a little bit more than half of what's released in terms of the energy comparing to the lithium here. So what we can conclude here is that as the size of the ion increases, the exothermicity of the process decreases. So this is due to a weaker ion dipole forces there. Now, if you look at the size versus the charge, lithium comparing to potassium, the size of potassium, the radius is about 133 picometer. Lithium is 78. So roughly, lithium is a little bit more than half of the size of the potassium there. Now, if you look at the positive charges actually reside within the nucleus. Okay, so the size of the ion there, you still have the core electrons surrounding the positive charge. So in this case, this negative electron cloud will actually repel this part. Okay, so the positive end is attracted to the negative end water molecule, but there is a longer distance between the positive charge and the negative end of the water molecule compared to lithium here, resulting in a difference in the amount of energy required here. And it also has something to do with the charges there. If you compare the size between lithium and magnesium there, magnesium is 79 picometer, lithium 78, so the sizes are comparable. However, you get 2 positive charges versus only 1 positive charge here. So the interaction between the water molecule, 2 more positive charges, you have a stronger attraction there, and you can see the quantity, the amount of energy involved in here is almost quadruple. In 2000, the 1922 kilojoules per mole for magnesium ion versus lithium ion, even though they are about the same size, but because they bear different number of charges there, and you can see the difference there. So again, as the ion size increases, the exothermicity of the process decreases, and this is due to a weaker ion-dipole interaction. Between lithium and potassium, you can clearly see that, and also remember the charges, the total number of charges also matters there. When you have more positive charges, resulting in a stronger interaction there, even though the 2 ions are about the same size. Okay, so that's the